Alrighty, I think we should get a move on. I think it's just gone 2 minutes past 4, so we don't want to keep anyone waiting. Um, on behalf of myself and everyone at MentaLab, I'd like to extend a very warm welcome to our first 2026 edition of the MentaLABS webinar series. Today, we are joined by the wonderful people from neuroTUM, who are from the Technical University of Munich, here based in the city, whereas exactly where our headquarters are also based. We're very excited to have them, so thank you very much for joining, Matt and Anna. They will be showing us some very interesting BCI related applications today in their presentation, and I'm very much looking forward to it, as I'm sure everyone else is as well. So just to give you a brief idea, MentaLab and MentaLABS is not actually the same thing, although they sound exactly the same. As you can see, MentaLABS with the capital LABS is standing for Learning About Biosignal series. And this is our dedicated webinar series meant to sort of connect us to the research community here in Munich, in Germany, and also on a global scale as well. So without further ado, let's move on. Today, I'd like to give you a brief idea of just the agenda that we will be following. So right now, I will just briefly introduce you to us as a team at MentaLab, but I'd also like to briefly tell you why we are doing this MentaLabs webinar series as well. Following that, we will have the presentation by neuroTUM, and the title of their presentation is A Community-Driven Approach to Enabling EEG-based BCI for Assistive Applications. And they have a lot of cool new things to show us from projects that they have done, a paper that they have published, and some really cool videos that go along with that as well. So very much looking forward to seeing that. And of course, following that, I'm sure there will be lots of questions and inquiries and curiosity related to the presentation. So we will be having a brief discussion and Q&A session where Matt and Anna can answer questions from the audience. So to briefly just tell you about us at MentaLab, we are a Munich-based mobile EEG-based company. And essentially what that means is that we manufacture and provide our research community with a very high performance, mobile and open source platform and biosignal amplifier. And this amplifier is extremely, as I said, mobile and lightweight. I think it's actually the smallest and most lightweight system on the market at the moment. It has a very long battery life. It has some really cool streaming capabilities, a very high performance system with different sort of sampling rates depending on which sort of wide or wireless streaming mode you're choosing. We have some very cool software that goes along with that. And of course, all of this is in a more open environment. So we really prioritize giving access to giving our researchers access to everything that they need, the raw data in a very open file format, and we have no subscription fees or financial costs associated with that as well, which I think helps a lot of research institutions globally. Our purpose at MentaLab is we have multiple purposes, of course, but just to name a very few of the key ones that we have, we are obviously mostly interested in innovation in the biosignal space. So we obviously provide our research community with this very high performance EEG or EXG system. And of course, this is with the goal to support research and development efforts around the globe. So we see our device used in various partner institutions spanning from the Americas all the way to the edge of Asia. And our device is used in multiple different kinds of applications and use cases, ranging from neuroscience to psychology, and of course, BCI, which is the focus of today's presentation. And lastly, our main goal of today's presentation as well, and our MentaLabs webinar series as a whole, is to really foster scientific exchange within the research community. We want to spotlight really cool research that is happening within our users ourselves, but also people outside of our direct reach. And of course, we want to explore future directions in the biosignal space as a whole. So enough about that. I'd like to also put the spotlight on our two speakers for the day, Mr. Matt Under and Miss Anna McWhinney, both who are from the Technical University of Munich, of course, with slightly different backgrounds. Matt is an electrical engineering and information technology graduate from TUM, whereas Anna is a biomedical neuroscience TUM graduate as well. So I will not go into too much detail about these two humans who are going to give us a really grand presentation today. I'm sure that they will briefly introduce themselves and neuroTUM as well. And without further ado, I'd like to pass over to them and they can start showing their screen to show you a little bit more about what they're working on.
Yes. Hi, everyone. I will begin. I will just quickly share my screen so you can see our presentation. Hopefully this works. Yeah, is that okay?
Yes,
Yes,
we can
it's
Hopefully
see
correct.
everybody
everything.
can see my screen. All right. So, hi everyone. I'm Anna. I will briefly introduce neuroTUM. As Sarah kindly introduced me, I will just add a little bit more about myself. So, I have been part of neuroTUM actually for almost 4 years. So, I've been here since the beginning. And I have a background in neuroscience and also neuroengineering. So, I've kind of used my neuroscience expertise along the way as much as I can in the group. And yes, neuroTUM has been a very important part of my life here in Munich and my studies also. So I hope you enjoy this presentation about it. And yeah, so our title today is a community-driven approach. Um, Enabling EEG-based BCI for assistive applications. So I think it will become a bit clearer why we chose this title, why we have this community approach to BCI at neuroTUM, and how this is one of the main pillars of the club. So just to start, this is our small agenda. So I will introduce neuroTUM. I will talk about the BCI side of neuroTUM because it's not the only thing that we do or have done at the club. Also, the Cybathlon, which we participated in and has been a big goal of ours. And then Mart will introduce neurorobotics and this side of the club too. So, in case anyone hasn't heard of us, maybe there's some neuroTUM members today. The club was formed in 2022, so I've been at the club not since the beginning, but very close to the beginning. And yeah, approximately 40 students from many backgrounds. Um, can you still see the presentation? Sorry.
We can,
Yeah.
but the presenting mode is
Oh,
off
sorry
English.
about this. There we
Yes, we
go.
can see it back.
And yes, so the main focus of this group is to bring students together from TUM and other universities um, to explore projects in neuroscience and engineering and really bring people with these interests together. So we have done and continue doing research projects, collaborations, but it's also a place to just meet people with these same interests and find a community based around this field. So our these are our main pillars, which I think have brought us to where we are today. We started the club as just a very small team with very large goals, and now we have different teams, different sub teams, and different things that we're working on that have brought us to newer and bigger goals. So as you can see here, I will now briefly touch on neuroTUM's timeline. So this is a very kind of broad overview of what we've done. There's obviously been a lot more, and I would need hours to kind of cover all of this. But yeah, I just wanted to introduce kind of how we got to where we are. And as I said, I will focus mainly on the BCI side of neuroTUM. So after the club was founded, it kind of quickly expanded to having various different teams, including the BCI team, Neuromotion, which is the robotics team, electronics, etc., as well as a very large part of a operational team, which is quite pivotal for a group of this size. So, as you can see here, in October 2024, we actually participated in the Cybathlon at ETH in Zurich. So, if you don't know what this is a very like impressive and large competition for assistive technologies that sadly no longer is organized. It used to run every 4 years, and it's designed sort of like a sporting event where there's different categories or races where you can participate as a group, as a research group, as a lab, as a company. It really depends on who you are. And we decided in back in 2022 to have this as one of our bigger goals. So it took us around 2 years to really set the technology up, to build our BCI system, build our team, also find our pilot. So for this competition, we needed a quadriplegic pilot to perform a series of games and tasks in the BCI race, so using our BCI system. And thankfully, we have Yoki, who is also a part of neuroTUM, who was our pilot and who could participate for us. And you will see in the videos later. So this is a super cool experience, and I will touch more on what we did and how we did it. But it's the emphasis of having this competition that really highlights advances in assistive technologies is a really big part of our goal and our motivation, and also this community aspect of bringing together people, including our pilot Yoki, to be able to build this BCI system with him as the center of it, and allowing us to have direct feedback from him and building technology really for people who will need it and use it. And yeah, I will touch more, give you more details, but this was like a kind of introduction to the Cybathlon. And then finally, really recently, actually last month, we published our findings in this paper. Which was also a very cool experience, very different. So we had to kind of consolidate our findings and our learnings from the Cybathlon, also with a lot of additional data collection with other pilots. But we were able to tell our story and kind of bring people to a place where they could read about what we did and how we did everything we did in the Cybathlon. So yeah, this was really exciting for us because obviously having published research is always cool. So that was the timeline for BCI. I will kind of just talk through the main, most important things, just so you can have an idea of this project. So, like I said, the Cybathlon was our main motivation for 2 years. And we'd seen the BCIs normally work well within labs, but in the real world, there's a lot of challenges that still make this technology not very usable. So portability, real-time performance, robustness, whether it's noise from the signal or just environmental noise or stress of the user. So this was kind of our main motivation and what we wanted to build for the Cybathlon, because the Cybathlon is a live event. So obviously there's high levels of stress. It's not the real world, but it's also not a lab. So you have to build something that is actually usable. And we always wanted to have this community aspect in mind where we're actually designing it for someone that actually needs it. So again, this emphasis on assistive technology brought us to participate and build this setup. So what did we actually build and what did we actually accomplish? So we built our modular BCI pipeline that does both online and offline processing. So this is a little bit of a sketch of what our BCI does. Obviously, there's a lot more details to this, but we acquired our signals using a portable EEG. We had several pre-processing steps of our data and then feature extraction and classification of our data to then, in the end, be able to play this game that the Cybathlon actually provided for us. So the game had a few control signals that you had to do with the EEG signal in order to pass the tasks. So the tasks included, for example, controlling a little avatar of a wheelchair to pass through a room, or press a button on an ice dispenser to bring ice down to a cup. And these were like gamified tasks that the pilot had to complete in real time. So this was the competition that we were aiming to build for. Here on the next slide, you can see a more detailed overview of our system. So the EEG setup, then we had a data receiver module. where all our data was collected. And then we have several steps, including filtering, artifact removal, re-referencing in order to pre-process the data, then also epoching and normalizing between sessions. Anyone that's worked with EEG data knows how variable and prone to change this data is. As much as we love working with EEG for its portability, it's non-invasive, of course, so it's easier in that sense. It's not the easiest data to work with. However, this was our setup, and actually, I believe 7 out of the 8 teams that participated in this BCI race were working with EEG data. There was only one that actually had the pilot had an implant. As you can imagine, his data was quite good, but this was our setup. And then after these steps, we had a feature extraction step to extract features from our data, and then be able to train our classifier. So after this, through the transfer function, we were able to have our control systems and play the game. So the main also advantage of our system is we had both online and offline. So our offline data was used to train, and then our online data was used in the Cybathlon and also out of the Cybathlon to play the game in real time. And yeah, this was a lot of work, a lot of different people with very different expertise. So, for example, me from neuroscience, and I was like more of a medical background. I was in charge of the experimental design. So, looking at what tasks the pilot had to do for data acquisition. So in this case, we used motor imagery tasks, which is imagining a movement of a certain body part and acquiring that data from EEG. And so there's a lot of literature on why motor imagery is used for BCI, especially for BCI using EEG, but this data is very similar to if you were actually moving this limb or this part of your body. And it's quite not easy, but quite easy to then classify. So we also tested a lot of different tasks and came to the conclusion that was the best one for us and this specific goal. So yeah, this was our system overview. We have a video here of our pilot completing the task. So you can see he's going to open the door and let the wheelchair go through. Yeah, that's Yoki, our pilot. Yeah, and so this is actually the game was provided to us several months before the Cybathlon, so we could train. And we also had an additional game that we used to train and to basically allow anyone that was participating, but specifically Yoki, because he was competing for us, to train how you do motor imagery, to be able to know when the classifier is classifying correctly, even though this is highly variable. And yeah, this was kind of our goal. So a really big part of BCI in neuroTUM is the human-centered design, like I've already explained, having our pilot as the center of our design. So using both training games, feedback screen, and this gamified training where he could train using several different games, not only the Cybathlon one, allowed us to really design this technology for our pilot and kind of listen to his needs, directly ask him what's working, what's not, what's more comfortable, what's less comfortable. And so, of course, we want our system to be very accurate. This is the point of having BCI. However, usability, actual people using this technology is also super important. So if you take the human out of BCI, it's just going to stay in the lab. It's just going to stay in research. And we kind of wanted to even just a little bit come closer to this goal of having someone actually in the center of our technology. And I think we kind of managed this. This is Yeah, it was a really cool project to do. And we were actually the only team competing in this race, in the Cybathlon, in the BCI race, that was fully students. So we didn't have any PhDs. Of course, we had advisors and people that helped us along the way, but the actual tech was built only by students, and we were only students there. And it's very cool to see people that are not experts in the field come together and be successful. Yes, so just the quick results. We always like to have some data. We managed, and this is what we published. So this was the Cybathlon data and also results that we had after with other pilots. So we had an offline accuracy of 84% and a real-time accuracy of 73. So I think when you consider that we've done this with minimal resources, again, we're just a group of students, then I think this is quite good. And in the actual competition, Yoki actually successfully completed one task, which was very cool to see. And the energy was really high when he did this. We were all cheering from our seats. And yeah, of course, on the day, it was a highly stressful situation for him, for us, for everyone. And we always have to bear in mind that there's real world variability. But it's also very interesting to see how this technology changes when you take it out of the lab. Uh, just a few pictures of what the Cybathon was. So you can see here some of the team. It kind of looks like a sporting event, which I think is kind of the point of like some sort of Olympic-esque event. But it was really good. We also got to travel all together and then celebrate after. And like I said, this was a huge deal for the club. And then after this has inspired us to do other projects. We're actually setting up another kind of Cybathlon inspired project with the University of Graz. So yeah, this was very cool to be a part of. And I think this is it from my side. So, Mart, if you want to share your screen.
Yes. Did you stop sharing? Yes, perfect. And can you see mine?
Yes.
Great. So let me continue. Thanks, Anna, for the first part of the presentation. And I also would like to introduce myself. So as Anna mentioned, we are from different backgrounds. I just graduated from my electrical engineering studies, and um, again, this whole club is based on the human-centered research, and at some point we had the urge to also build something that manipulates objects in real life, where we always had the focus on playing games with the brain-computer interfaces and control some simulation environments with it. But this time we had the idea to dive into the world of neurorobotics, and I want to give a short introduction about the Wikipedia explanation of neurorobotics, so to say. And it's a combined study of neuroscience, robotics, and artificial intelligence. And as you may know, or if you're following the recent updates, all these fields are kind of merging in a sense. Of course, robotics, artificial intelligence are widely used, and basically what neurorobotics is also including neural systems and brain-computer interfaces into that system to control an external object. Of course, when we say robotics, it's not always a robotic arm that we mentioned. It's also exoskeletons or EMG research that also is actually the biggest part of that research. And I would say brain-computer interfaces is just entering in this field, since the neural networks that we kind of sold is helping quite understand how this different patterns in the collected EEG signals works. And basically, we are also focused simply on the EEG-based brain-computer interfaces, and we are not doing any EMG research. That's why I will explain everything in the robotic arm control field, which we are more experienced in. So what's our goal? Basically, we had the idea to build a wheelchair-mounted robotic arm to enable people with disabilities, again, to wander around the city, like do tasks that are manageable by a robotic arm, such as calling the elevator, holding a cup, drinking out of it, opening doors. things that those people need constant care for, but is actually executable by a robotic arm. And of course, although these tasks sound easy, there is also the fact to consider that the brain-computer interfaces are not accurate. So Anna just showed the accuracy we got in the Cybathlon race. And of course, 73% accuracy is insane for brain-computer interface research. But if you have a robotic arm with 73% of accuracy of what you want to do, then it may be annoying. And of course, BCIs are closed loop systems. So if you are annoyed, you produce different signals and the whole loops is not working anymore. And exactly, we have the EEG-based BCI in the main point of it, and I would like to explain a little about how we are trying to solve this BCIs being having low accuracies and latencies, and them working together with a robotic system. To do that, like exactly, I want to also show a little some pictures about our team and what we developed so far. You can see a neuro-robotic arm. This is a challenge we just participated in, and neuro-robotics gave us a robotic arm and enabled our project, so to say. And yeah, you can see also a friend of ours having fun with it. So I would like to first explain the concept of synchronous and asynchronous brain-computer interfaces. If you have a computer science background, those two words may mean something different than what it's being used for in BCI field. Basically, synchronous and asynchronous BCIs they differ on the classification method. So basically, in synchronous BCIs, you know at which time period you need a classification for. For example, think of playing a game. We implemented a dino game, if you know it. If you don't have internet and if you open Google, you get this dino game where you can jump or duck to avoid objects. And for example, this game can be implemented on before the cactus. It asks the user if he wants to jump or duck. And you know that you need to classify this behavior or the idea of jumping or ducking right before the cactus. So you know when you need to classify. And there's also asynchronous BCIs where you don't know when a specific command should be given. So you should also be classifying the null state. Basically means that if you are not thinking of jumping or ducking, the system should also be able to provide the classification that you are not thinking of it, which is actually most of the time. So a misclassification may lead to more problems in this case. And of course, synchronous BCIs are widely used for applications, but when it comes to robotics, we need things more asynchronously in a sense that you never know when the person wants to drink something. You never know when the person wants to open a door. So it should be actually asynchronous. And that's why I added this red pill, blue pill reference from Matrix, of course, and apparently like this is what I found in Google, but I hope it's true. Basically, red pill represents the choice to learn and an unsettling truth about reality, while the blue pill is the option to remain comfortable ignorance. And in the case of robotics, I will say synchronous BCIs are comfortable, but it's sadly is also ignorance. And that's why we try to enable an asynchronous system work together with a robot. So how we manage that is basically we have this asynchronous system, but when you are thinking of controlling a robotic arm directly, you should be able to classify vectors, right? So for example, going up, right, left, down, and like giving the robotic arm a direction. So in case of brain-computer interfaces, as Anna also mentioned in her presentation, they are very noisy systems, and they are actually also measuring electrical activity on your scalp, and they don't have single neuron precision. So you may be thinking that having an electrode on your motor cortex may solve everything and you can just classify moving right, left. Well, the problem is it's not always that accurate, especially if the system is asynchronous. So of course, in this case, misclassification means the robotic arm can move anywhere, can cause harm in the society. And this is, of course, something we need to avoid. So basically, there are many problems with the direct control of the robotic arm. You also are collecting data from this EEG. So the classification that you make is delayed. So maybe you are thinking of moving right at that moment, but the robotic arm starts moving seconds later, and that's a problem. Of course, this specific behavior can cause frustration. And as I said, BCIs have the brain and the signals from the brain as a part of a closed loop system. So if you are frustrated, you literally can see that in the EEG signals. And this, of course, affects your classification accuracy. And it also depends on the environment you are in. For example, the noise patterns in a U-Bahn may look different than a lab. So how do you then ensure the safety of the person and its environment? That's why we kind of developed a system that's semi-automated and also asynchronous. So basically what I mean by this is it's not that you think that the robot should move right up, down, or should move into a specific direction, but you work with the robot together to give it an end action. So basically, for example, a camera classifying objects that it can manipulate in its environment, such as a cup or a door, and it updates a graphical user interface saying, hey, I see a cup, a door, and whatever in the environment, and asks the user to give it an action using this brain computer interface, such as give me the cup or open the door. And the robotic arm executes this action on its own. Which is exactly what the direction of robotics research is going into. If you guys are following it, there is this huge Beijing race that humanoid robots just run themselves. There are many open source projects now that huge amounts of data are collected to hold a cup or open a door. And these are exactly ideated to be done automatically and not by external control of things. What we are trying to enable is that this command is given by the user using a brain computer interface. So it's the command and the control is coming from the source of the intention. Exactly. So here is a video of me playing tic-tac-toe with a human using this robotic arm. And this was the project we developed. So basically the difference in the brain computer interface, you can already observe that I am not thinking of moving left or right, but I am simply looking at LEDs, which are not blinking right now, but you will see after the robotic hand executes its action, they will start blinking again. Look, they did. Basically, I am navigating inside this grid to give the robotic arm the end destination of where it should draw a circle. And I am not controlling it right now by thinking of drawing the circle, but I just gave it an end action to execute. And this is exactly our idea about the future tasks too. Of course, this is a two-dimensional workspace. It was rather easier to implement than opening a door, of course, which is a huge challenge on the engineering point of view. But the idea is the same. So it's semi-automatic controlled and it's asynchronous. So you can give commands at any time. Exactly. So I cut the video short because I actually lose. So I like spent 6 months developing it. I never won a single tic-tac-toe game because I am simply bad at tic-tac-toe. But yeah. So that was all on the neuro-robotics side. And thank you all for listening. And here you can find some QR codes for our Instagram, LinkedIn, and our website. Feel free to check our content. We are quite active on LinkedIn and Instagram, so you can always follow our application period, or if you are interested in the field or if you want to support us, feel free to contact us. And yeah.
Thanks so much for that, Matt and Anna. It was really awesome listening to that. I will quickly share my screen now to go to the Q&A section. There you go. So, yeah, like I said, thank you very much. I found that incredibly insightful, a nice short and sweet presentation that really gives us a nice overview of what's happening in the actual space of BCI and also what you guys are working on at neuroTUM, which seems like a lot. I'm not sure how you managed to fit everything into your schedules, but I'm thoroughly impressed, and I'm sure many of the watchers here today are also. But I don't want to take up too much space here. I want to open the floor now for any questions that the audience might have. There is no option to unmute your mics at this point, but please feel free to share your questions in the chat or the Q&A box, and we can read them on our end to Matt and Anna, and I think they also have access themselves. So anything that you're curious about, please feel free to get typing. Perhaps I can start out with the first question. It was first directed at Anna, Anna's section of the presentation. So I saw in your processing pipeline that you guys are obviously removing artifacts with ASR. So there's obviously, lots of different ways in which you can sort of clean the data to really get a nice signal out of it. A lot of people I've noticed are also using ICA in this space, of course. And I was just curious to know I guess from a theoretical point of view, which would be better to clean data that is specific to your use case for BCI? And what is maybe the difference? Perhaps you can start out with just explaining the brief difference between them.
Yes, so actually we have tested both. So ICA is quite a common method to clean data. ASR was a bit more of like an experimental route that we took. I am not the person to ask about these methods, but I believe ICA it works well for different applications. So ASR basically takes the data and reconstructs it into another subspace. And from what I have understood, this is a lot better for motor imagery. So the main issue that we had is ICA was not cleaning the data well enough for our motor imagery data. So because we focused only on motor imagery, again, motor imagery is taking data from the motor cortex, but only imagined movement. So we kind of tested a few ways of cleaning our data and pre-processing our data, and we found the ASR slightly outperformed other methods like ICA. But yeah, that's a good question. And I think a lot of our work during the past 2 years before the Cybathlon was testing out different methods because there are so many methods that are published already for pre-processing. We did a lot of filtering work as well. We played around with epoching in different ways. So yeah, but was kind of like the best combination that we could find that worked for motor imagery. Yeah.
Yeah, that makes a lot of sense. Is there something you wanted to add, Matt, about that? I see you've unmuted.
Yeah, one slight aspect on top was I think the ASR method was specifically chosen to be performing better in the online application. So basically, ICA requires a bigger window to be able to understand the noise pattern in different channels and to denoise it. And ASR is something that you kind of pre-train on pre-recording. So you basically record a session before the experiment itself, and it's basically calculating the mean and the variation of the data, and it's quite real time. I would say the performance on the denoising was worse, maybe, but the real time aspect in our case is more important. I never worked with the Cybathlon pipeline, by the way. That was just what I heard about this two different approaches, and the reason I think neuroTUM chose it was also the real time aspect of the computation,
So
which
we
is not that quite often be done in BCI research. There are many offline experiments, and the field is expanded in that way, kind of, and we try to adapt it back in the online field, kind of.
Yeah, exactly. So I think a lot of the kind of more established methods like ICA are commonly tested offline, but we for the Cybathlon we needed to work online. So it was always this kind of play around with the established methods, what the research has already done, but then also testing and having this robust or as robust as we could online pipeline. Yeah.
Yeah. That makes a lot of sense. Thanks for actually clarifying that for us. We had a few discussions in office about this difference the other day, so I was just curious to get your guys' perspective on it as well. Of course, it very much depends on the research domain in which you're working, which method
Mhm.
works better, but of course, some people stick to one over the other. But for you guys, it seems to be working out pretty well, it seems. Um, yeah, I think other than that, I also had a second question, if you don't mind me taking up a little extra time. Um, so your accuracy results from the paper that you published, you said that you were obviously working with low resources, so it's not the typical environment in which a researcher has everything at their disposal, all the finances behind it as well, all the time and the energy as well. But for you guys, you still managed to get, I think, an 84% accuracy with your system. So I was curious to know, what is this accuracy rate in context? So for you guys, you say it was low resource. So 84 to me sounds really great. In a more standardized lab environment, in these perfect real world, perfect lab scenarios, what would an accuracy really look like? Accuracy rate.
Yeah, so that's a great question. Actually, for us, and as far as we've worked with, when I say that we had low resources, obviously there's, time and having I think having time to do the experiments and take time out for data acquisition is always important. But I think for us, our hardware was maybe not, the best that we could have had. We were actually super grateful because we had hardware kind of donated to us from a company or lended to us from a lab. But obviously, the more electrodes that you have and the kind of more you invest into hardware, especially EEG, because it's so variable already as a data type. You're not, you have this distance, you're not going into the brain. So the more that you invest on this side, the better your data is going to be. So I think when I say that we had like low resources, it just means that we worked with the best data that we could, but the data quality could ideally be a lot better, which I think is what EEG labs have. So they might have different hardware types for different environments or for different applications, and we simply didn't. Also, I think in terms of time, having just more volumes of data. So as I said, we're the students. We had a few different pilots, not only Yoki for the Cybathlon, but we had a few different team members that would volunteer to take part in the experiments, me included, even though I have the worst hair for EEG. Um, and so, yeah, I think these two things are really important when you are doing this type of research. So, if you were to work in a more professional setting, in a company, in a lab with more resources, you can get classification accuracy of in the 90s, right? And of course, there's always a difference between offline and online. But yeah, the kind of other labs, it does go up to 90 something percent. And of course, when you see 70 or 80, you think, okay, that's good. That's a good number. It's not a bad number. However, if you think about it in this kind of human-centered aspect, you would ideally want your classification if you're doing a task that you need to do to be as close to 100 as you can, right? If you're kind of thinking about, okay, can I use an EEG BCI system in my day-to-day or even a robotic application? Even though 80% or 70% sounds good, it's not perfect. But I think also for whoever is interested, we also talk about this a lot in the paper. Again, this is not my specialty, but we tried different classifiers. So I think the one that got the best results was our deep learning classifier that the team spent a lot of time on, but we also compared it to other machine learning methods, and this was also the scope of this project to kind of see where we were as in methodology wise within the field, and yeah, this is what we kind of came up with.
Yeah.
Yeah.
That makes sense. You said also that, these rates do go up to the 90s. Is there a chance this rate could also extend to like the 99s and 100s, or is this completely just not feasible in
I mean,
that context?
as far as I have read and seen, getting it to perfect classification is quite hard. I think to get to that, not only do you have to have a great classifier, great training data, etc., but you also have to really have your tasks kind of on lockdown. So motor imagery, for example, can be trained. There's actually a lot of studies that talk about training motor imagery, talk about different people with different backgrounds. So, for example, if you have played the piano a lot in your life, you have very fine motor dexterity, or you're an athlete, or things like this, you will have different type of motor imagery kind of accuracy in terms of how well you imagine these movements. Also, very, very importantly, when you're working with people with a disability or quadriplegia, I can never say that word, then you have to adapt your system to these people.
Yeah.
So I think to get this like perfect accuracy, there's just a lot of different steps that I think have to kind of interplay perfectly, and I don't think we're there yet as a field. But
Mhm.
anyone who knows, maybe correct me if I'm wrong. I'm not an expert, but yeah, there's just too much to work on, what is what
Yeah.
I'm trying to say.
That definitely does make sense. And I think it ties back to the whole idea of this human-centric design, right? You have to take into account this inter-individual variability that obviously
Totally.
is at play as well. I think that
Mhm.
is a major theme with BCIs that is definitely not focused on enough, but it's really nice that you guys are actually taking the initiative to focus on it. So
Yeah.
thank you. We do actually have another question from the chat. I'm not sure if you guys can see it, but if not,
Yeah.
I'm just going to briefly read it to you. It says, "Hello, Anna, and hello, Mert. Thank you for your great presentation, of course." And he wants to know, or he or she wants to know, are you still actively collaborating with your current pilot? And are you still in contact? And what are the next steps for expanding the system's capabilities? So maybe you can start out with the first, that
Yes.
question.
So, our pilot Yoki is actually not just our Cybathlon pilot. He is a member of the team. He's a neuroTUM member. He's actually also a medical student, so he's studying medicine. So I think currently, as far as I'm aware, I think he's more focused on his studies. But we are still in contact with him also because through this experience, a lot of us have become good friends. So there's a lot of people who meet and collaborate externally from neuroTUM, and yeah, as far as experiments, Mert, maybe you can correct me if I'm
Maybe I
wrong.
can answer that. Exactly. So we are also trying
Yeah.
to also time to time arrange experiments with him, but
Yeah.
as Anna said, he's also studying medicine. Like
Yeah.
we sometimes also can't find time to
Yeah.
neurotum, and the same is happening time to time. But we are, of course, still in the same team, still in
Hmm.
contact, and basically that also leads us to the next question of yours, how the expand the system capabilities look like. So we are constantly also working on the pipeline itself and to clear the signal processing steps that Anna showed, trying out different ways. This is, of course, the way we chose in a restricted time to compete in a competition doesn't necessarily mean it can't get better. So we are basically focused on observing what we actually did, because it's not always that straightforward to understand how your signal processing looks like. And also on the other side, collect more data, because this is kind of how all artificial intelligence related fields are expanding. Also on the robotics side, people are trying to collect data so the models can generalize better, the foundational models looks better or more accurate. And of course, that's also what we are trying to do. We are also trying to build our own experiment management base. It's more like how the club is storing this data, processing it, or like ensuring its quality. And of course, that's why we are also trying to always organize experiments with Yoki, where it's not always the same motor imagery signal that you get from people with quadriplegia and people that uh, I don't know, that are athletes. Of course, there's a difference in the signal, and what we are trying to do is, of course, to include all in our training data set to hope that the AI can generalize. But yeah, it's maybe I can say that we are not purely in the hope of a AI model to generalize, because the field of EEG research is also highly on this real-time signal denoising, and that's as Anna showed, has a lot of steps, a lot of design choices that you can make, and basically we are trying to also understand how this design choices affects or classification affects our system, and also the speed, because exactly. We always talked about the accuracy, but the classification speed is also something that's quite important. Yeah.
Just so I can add some little detail at the end, I think also because the Cybathlon, so this is purely the BCI part of neuroTUM. I don't want to say that we're not doing other things, but for BCI, since we had the Cybathlon as our goal, and sadly the Cybathlon for now is not being reorganized. We're actually organizing, I think I mentioned before, another competition where teams are going to compete in BCI games, just like well, not just like the Cybathlon, but we've taken inspiration. Um, and yeah, so this is our main kind of goal, which is later on in the year to be able to bring our BCI pipeline, hopefully, better than it was before and with more capabilities, with higher accuracy if possible, to this new competition that we're now in the process of organizing. So I think it's cool as a group to have this kind of goal to work towards. I think it worked well in the past. And yeah, this is kind of our next big step, so to say.
Fantastic. Yeah, that sounds very exciting. I suppose it might be too early to ask as well, but would you plan to also sneak a publication into that like event afterwards, or is it too
Maybe.
early?
That's always nice,
Yeah.
it's I think writing a paper and everything that a publication entails is cool as an experience, just as a potential future researcher. And it's also nice to receive recognition from, a journal or a chair, a group,
Mhm.
for all the work you've done. I think that's what we felt when we finally got this published. It's also good to receive feedback, which you always do when you publish. So yes, maybe potentially, who knows?
Oh, that's
Um,
awesome. Yeah, we look forward to it. Hopefully one day soon we'll keep an eye out for it. Um,
Mm. Maybe I can
yeah,
answer Salman's question,
yes.
if
You
that's
can see
okay.
the question. So just in case the other audience members can't see it, I'm just going to briefly read it out.
Yep.
Um, could you please elaborate on the latency requirement for your real-time BCI classification system? I'm just wondering if you had any certain number to achieve or not.
Mhm. So basically, I didn't work on the motor imagery side. Maybe Anna, you can answer that better on that side. The robotics side kind of work more on the SSVP, which is another paradigm to work with. What I can say for that part is that the average classification time for the SSVP side was 2.5 seconds, which basically means you start looking at a LED blinking, and 2.5 seconds later, we were able to tell which one we were looking at, which is not exactly real time. If you ever worked in a hard real time system, it's like the processing speeds that humanity achieved on silicon basically like indicates that things can happen in nanoseconds, and such models can also run in that speed. The problem with the BCI research mainly is that the sampling frequencies of devices are not super high. It's not always also the sampling frequency, but also the interest of frequency bands. So you are basically analyzing alpha beta waves, which are in 10 or to 30 hertz range, which basically requires you to collect seconds of data to be able to observe anything. So it means that, of course, you are thinking of something, but you are also filling a buffer that those samples are processed in, which means that you kind of require 2 to 3 seconds of information to be able to classify what you are doing, which is, of course, a pure latency to your system. So when we say real-time brain-computer interfaces, it's definitely not hard real-time systems where you can't even, process the speed of the system, it's quite slow in that sense, and that's also something that we are trying to solve, address, or work around. Maybe on the motor imagery side, you can add more, Anna. I don't know.
Yeah, so just briefly, again, all the details of this is in the paper, so maybe we can also provide a link to anyone who wants to read more about this. Latency is a huge, I don't want to say problem, but it is a challenge for online BCI, and especially in this competition scenario. So what we kind of came up with, just to kind of explain our results, we had computational latency and methodological latency. So overall, we had around 1600 milliseconds of latency, which is something we could work with, and we did work with. But again, this approach to testing out different pipelines, different methods, different pre-processing steps, different classifiers was also to measure the latency and somehow have it as low as we could. So yeah, this was kind of the number that we were working with. I hope maybe that's gives a little bit of insight of what we were doing. Yeah.
Also, as the last question, I'm wondering if you had any certain number to achieve. So we didn't have any number in
No.
mind about latency, but what I can say is if a system works faster than 200 milliseconds, the person's perception fe feels
Is
it as
fine.
a real time.
Yeah.
It's quite fine. 200
It's
milliseconds
quite
is,
fine.
yeah, too good for a BCI research to be. I didn't even read any papers that reached that, but maybe there are. I just didn't read enough. I don't know. Uh, but yeah, I can say that 200 millisecond is a perfect goal to reach in case of
Yeah.
usability by the person.
That does make sense, I think, from a physiological standpoint. I think 200 milliseconds is the average like re response time to a
Mhm.
stimulus. So yeah, that does definitely make a lot of sense.
Yeah.
Yeah, it sounds like there's a lot of complications and details that go into these projects. So thanks for taking the time to explain them to us, because I don't think anyone on our side, or at least I'm speaking on behalf of myself, I've never done a BCI related project. So there's lots of nuances that I've never been aware of that I'm quite aware of now.
Mhm.
There is a question, one more question. I think we have time for it. So, Annalie asks, she wanted to ask what training or level of training is required for someone to use the system effectively.
This is a great question, and I think it's a whole part of the BCI field, training for these types of experiments. So, um, required training, I would say you don't have to train to do motor imagery at least. So how the experiments work is you look at a screen, and when you have a certain cue, that is your cue to imagine a movement. So it can be, for example, moving your upper limbs, moving your lower limbs, or there's other motor imagery such as mental arithmetic, where you have to do mental multiplication, or imagine, we had one that was imagine the taste of a lemon, since this is kind of a universal experience. So I think most people, when approached to do this, could do this, right? But the kind of what the training does is, one, it trains you to imagine certain tasks in a similar way every time, because obviously an arm or a leg can be moved in very different ways. It can be continuous, it can be slower, it can be faster. So what we wanted with training was to have this signal as kind of coherent as possible. So you're imagining the task in the same way every time. Um, yeah, this was the kind of training that I don't want to say designed, because it's been done for in many different labs that do EEG. They also train, but it was just so that we could get the most consistent data that we could. And actually, we did find that the data was a lot better and more consistent for people that had trained. So our pilot Yoki obviously did a lot of experiments, but then there's certain members of our team that also just trained because they did so many experiments, and their data was a lot better than someone who has done it maybe for the first time. So yeah, it's so that the motor imagery itself is just consistent, and you don't kind of struggle to say, okay, how do I imagine this? I could do this in many different ways. You find out what's best for you. Um, I will also say that in our case, and I know in a lot of different cases in other labs, doing these types of experiments is quite fatiguing. It's quite exhausting because you have to imagine things repeatedly. You obviously have rests in between, but it's a lot of mental work to do this over trials. And like I've mentioned before, having a big volume of data is important. So our experiments would be quite long. So I think training, like in any kind of discipline, the more you train, the more used to something you are, and the more you can endure a task. So I think this is getting used to an experiment, but also knowing that, okay, today I have upper limb and lower limb motor imagery, and I know exactly how I have to imagine it, and my data is going to be the most consistent it can. Because obviously there's other factors, your stress level, what you've eaten, how tired you are, etc., that are also going to change your data. But the training is just to make it as best as you can in a kind of controlled way. But yeah, this is something that we just played around with. Also for Yoki, our pilot, it was to test how comfortable he was doing different combinations of tasks. And so training is just a good practice, I would say.
Of course. Thank you. That was a very nice, comprehensive answer to that question. So I'm
I'm
sure
glad.
Annalie is very satisfied with that.
Hopefully that was good.
Perfect. I don't see any other questions in the chat unless one pops up in the next few seconds. I think we should call it quits for the day. I think we are at the end of our time. But if one does pop up in the meantime, I will quickly slot it in. But if not, I just want to say again a very, very big thank you to you guys for presenting to us today. It was extremely fascinating. I'm sure I'm speaking not only on behalf of myself, but of the entire audience. It's really fascinating to see what you guys are up to, and we are wishing you all the best with your future projects. And we are definitely looking forward to what comes out next from you guys. We are, of course, in the city, so we will keep a close eye on your progress and your developments. And yeah, it will always be good to stay in touch. So, just overall, thank you very, very much. It was fantastic having you today. And without
Yeah.
further ado,
And thank you to all
Yeah,
of you
thank you
too
to
for
anyone
inviting us.
listening. Hopefully it was useful and
I'm
entertaining.
sure it was. I mean, not everyone can speak. I'm taking all the voices here, but I think
Yeah.
I'll speak on behalf of the general population here. Thank you very much. And
Yeah,
please, this is addressed to the audience. Please feel free to reach out to us at MentaLab if you have any other questions related to this presentation, but also if Matt and Anna will allow to reach out to them if
of course.
they're interested as well. We will, of course, still be watching your developments in the next few months and years, and we look forward to hopefully connecting with you guys again soon.
Thanks a lot.
Thank
Great.
you.
And for the audience and everyone online, please stay tuned for the next MentaLABS webinar, which will be happening at the end of May. There is no set date for this yet, but we do have a very exciting presentation for you in store for that one. So if you're around at the end of May, it will be at a similar time, similar date as to this month, and we hope to see you there. Thanks very much for your time, everyone, and wishing you a fantastic sunny week ahead.
Goodbye, everyone.
Bye,
Ciao.
everyone.